All right, good morning, everybody. We'll go ahead and get started. Be respectful and honorable of your time. Thank you very much for taking an hour out of your day to learn a little bit more about URETEK Holdings, kind of what we're doing, as well as some of the different partners that we have to really put together a complete package, a complete solution to help you and your customers manage your infrastructure needs. We put together this outside-inside series and have done some webinars kind of in the theme of having to treat both the outside and the inside series, why it is important. And so today we've got special guests, if you will, some partners that we have partnered with called Inversa, who show you how to accurately know that you need to treat the outside of the pipe. So we'll talk about them in just a little bit, and we'll go through a few administrative notes as well as share a little bit about URETEK Holdings to kind of reset the outside-inside webinar series. First of all microphones will be muted. We're going to have over 100 people here on this webinar, so just to minimize background noise, everyone will be muted. I think all of you have probably done a webinar before, so you're familiar with how to raise your hand. But in the GoToWebinar toolbar, there is a way to raise your hand, type in the question, and then we will address questions at the end of the webinar just due to the amount of people that we have joining us today. We also will be doing 1 PDH credit today, so there will be a follow-up email that will be sent after the presentation. If you could please provide some feedback of what other items you'd like to learn about or how we could better serve you, and then also that will trigger your request for a PDH on that form. As I mentioned, my name is Corey Carlson. I am the President of Sales for URETEK Holdings, and really have a background that kind of helps with all the audience that's on the call, where I've worked for a civil engineering firm, Burns McDonnell, for a few years, and then I was with Contech Engineering Solutions for 10, just providing different solutions for municipalities and engineering firms, and then been with URETEK Holdings for the last couple years. URETEK Holdings, we are a kind of a unique contractor in the fact that we've got sales engineers throughout our 31-state territory, where we are working with engineers, municipalities, to help drive spec, because we've got a couple unique solutions, and have over 25 years experience. There's been over 85,000 installations using our chemical grout, and we're also a contractor that prides himself in a safety culture with a very low EMR, as well as the ability to insure and bond our projects. And we are headquartered in Florida, but in involvement across the 31 states. So why did we do this trenchless webinar and kind of put together this outside-inside series? We all hear about the aging infrastructure, and it's $3.4 billion was identified in an article in February 2012, and 50% of the solutions are a trenchless technology, whether it's a slip line or cured in place. And so we've always paid attention to the inside of the pipe. However, we're not taking care of the outside of the pipe, which at the end of the day is the root cause of the issue. So with our outside-inside series, we will treat the outside of the pipe with the URETEK, which is our chemical grout. On the outside, we'll fill the voids, displace unwanted water, increase the bearing capacity of the soil using the chemical grout. And on the inside, we are an applicator for Centripipe, where it's a centrifugally cast concrete mortar, and so there you're able to get a like new solution for your customer, or in fact, if you're the municipality, for your own assets. So here's an illustration of kind of the importance of treating the outside of the pipe. Here on the left, you see the picture of a manhole. And most people, if they don't pay attention to the outside of the pipe or the outside of the manhole, they'll just figure that they need to do a kind of a mill and overlay for the asphalt. The road has started to settle, so let's bring it back to grade and move on our merry way. But the reality is, if you were to kind of look at this with x-ray glasses, you'd be able to see that there are voids underneath the pavement. There's voids around the manhole and the lateral line, but also a lot of this is all at the fact of this small little crack that's in the lateral line. So what'll happen is that crack will bring in the fines, and the soil will start to migrate down. Thus, the soil will start to settle. And now you no longer have your original bearing capacity. So even if you just reline this only, you have an inferior soil envelope for the structure. Which takes us to the difference between new design and rehabilitation design. In new design, everything is perfect. You know what type of pipe you're going to be using. It's in perfect condition. The joints work, the gasket or the bell and spigot, everything is lining up perfectly. From the surrounding soils, you can specify whichever type of soil you want. It is then compacted to your desired compaction level, 90% or 95%, whatever compaction level you're desiring, and all that goes into play. But what happens is there's unplanned water that starts to migrate through the system, whether it's due to poor backfill. Maybe some of the short pipe sections of RCP have started to adjust and move. You also have joint failure, no matter what type of pipe that you have. So then that brings us to rehabilitation pipe and soil design. A lot of us are familiar with CANDY, with the Culvert Analysis Design Program, that states that you need to take into account not only the structure, but the surrounding soil envelope. They are codependent composite structures where both rely on each other. Even RCP pipe, when it is in fact designed to take a lot of the load, if the surrounding envelope is not in good shape, it will start to settle and become misaligned. So what we have found, and really what is critical to the success of rehabilitation, is not only analyze the existing pipe, not only take into account any hydrostatic pressure, but it's really that surrounding soil. What is the condition? Are there voids? Are there issues that we need to address? This is a perfect case study of how critical the outside of the structure can be. March 2012, Trenchless Technologies had an article for a massive manhole project that took place in Chicago. You see this picture on the right. This manhole was lined with permacast, which is one of the products that we are also an applicator for to treat manholes. But you can tell by this picture, the soil surrounding the manhole failed. But that old brick manhole is standing due to that liner. So with this project, it was all about just doing reline for the structures, and the outside was neglected. So we'll go through a couple of quick slides here of how URETEK can help with the outside, as well as Centripipe on the inside. But really the whole purpose of today's webinar is to educate you on how do we detect our voids. So for the outside of the structure, URETEK Holdings, we utilize a chemical grout. Our chemical grout is very lightweight, but yet high strength. In the commercial industry, we use it to lift buildings, to lift footings, to improve bearing capacity. So very high strength to low weight. It is also NSF 61, therefore can be near potable water. And one of these case studies that I always like to share is this one in Florida, where the voids around the pipe had became so bad that we needed to treat it with chemical grout. But this is a natural spring for manatee migration. So that NSF 61 and that sensitivity being in blue streams for the Corps of Engineers or being in manatee migration comes into play. The whole purpose of treating the outside of the pipe is to make sure you don't have catastrophic events take place, and then taking care of your pipe. This picture on the left is sinkholes at the surface that were caused by I&I, inflow and infiltration. And the picture on the right shows basically we call it outcroppings, where we inject the chemical grout on the outside of the pipe. It starts to flow in, filling that joint, giving a positive seal. We then will clean up and dispose of those outcroppings. Here's a project in Cincinnati, Ohio, where a partnership with Inversa will come into play very well to analyze the voids on the outside, as opposed to, not knowing, for the Ohio DOT, not knowing how many voids were on the outside of the pipe. This would be a good one to help give asset management to the DOTs. Another way that we treat the pipe for that outside-inside is through Centripipe, where we are taking care of the inside of the structure. So now we've talked about how to treat the outside, and here's a way to treat the inside. And permacast is for manholes, and Centripipe is the same technology, just turned horizontally to take care of the horizontal lines. This can be used in sanitary and storm sewer, and is currently approved by 14 different DOTs across the country. And really, that's just a function of paperwork, and the fact that filling out the paperwork and applying for different DOT approvals is just a matter of the exercise of getting it approved. So here you can see a picture on the left. That invert is deteriorated, and so we will pour 12,000 psi flowable fill, and then to give a level surface plus fill those voids. But on the inside, we will then spin a high-strength mortar of 8,000 psi to the desired thickness. The thickness of our Centripipe is determined based on the criteria of the site. What is the loads that it will see? What's the depth? Where is the water table? But the Centripipe thickness is designed to stand alone. It is not dependent of the host pipe. That host pipe is really just considered to be a form for the mortar to apply to. Here's a couple quick project profiles just to show this was a job that was hand applied using the same mortar mix but hand applied. And then here is another application with a DOT to help take it from an older pipe that was buried deep, and now you can treat the inside. So really, to kind of recap, URETEK and Centripipe fix the void in pipe after the problem has occurred. So we can use the chemical grout on the outside, the Centripipe on the inside, but what we're trying to shift is the asset management with municipalities as well as those engineering firms that work with them to have a maintenance schedule before a problem occurs, before that sinkhole on the surface has happened, before that manhole is settled in the roadway, so that cities can plan financially for their assets. And so that's why we partnered with Inversa, because they have a first-in-class technology to detect the voids on the outside of the pipe, as opposed to just going with your traditional, either acoustic or visual. They've got basically a CAT scan system that is very useful in helping. So these three solutions together are definitely going to reduce life cycle cost. So now I'd like to hand it over to Dallas McCready, who's in charge of business development for Inversa. And thank you very much for joining us, Dallas, as well as Steve McCormick, who is in charge of product development technology for Inversa. So now we'll hand over the screen to Dallas and hopefully have no technical challenges.
Thanks very much, Corey. Okay, it looks like it's loading up. So thanks very much, everyone, for joining. As Corey said, I'm the VP of Business Development for Inversa. Also on the line today, we have Steve McCormick, who's our lead technical engineer, and Alex Palmer, who's our market analyst. And there's a great opportunity for us to explain a little bit about Inversa, our company, and our unique technology, and also learn about the challenges and opportunities within your respective communities. So Inversa, we have two primary markets. We have the oil and gas, predominantly the offshore oil and gas, and then civil infrastructure, which will be the focus of the conversation here today. Ultimately, our objective is to extend the service life of assets and maximize budgets on behalf of the asset owner, and we try and do that through a proactive asset integrity management system. We have patented technologies and procedures that we use to help shape our asset management programs, and we specialize in corrugated metal pipe. We do have the ability for some other assets, but our specialty really is around corrugated metal pipes and storm systems, roadways, and roadway culverts and levee systems. In terms of our organization, we have a very solid team of multi-disciplined engineers and technicians that we've assembled. We can support existing markets with that, but we also have a constant R&D cycle where we're trying to take this technology into developing new applications and new opportunities for the technology. We're capable of providing value-added engineering. As you can see from the slide, we have a diverse mixture of folks on the engineering side as well as technicians, and also collaborating, and many times we collaborate with the engineer of record or the local engineering consultants to try and help solve problems within for the assets on behalf of the asset owner. In terms of some of the projects that we've done, we're extremely proud of the diverse mixture of clients and the projects that we've been exposed to and had the opportunity to work on, and those have really validated the value of Inversa. And now, as Corey said, we're exploring some of these partnership opportunities to try and go out and really penetrate the market and grow the awareness of our technology. So we're happy to be working closely with URETEK to accomplish that. So you see the a broad mixture of clients from the U.S. Army Corps of Engineers, large municipalities, small municipalities, state DOTs, private land owners have used it, as well as Florida management projects. So as you can tell, we've really done a very broad and diverse mixture of projects throughout North America. In terms of the challenge, the state of the industry, it's no surprise to anyone. Really, we have a lot of aging assets with limited budgets. So really, one of the trends that we're seeing emerge is trenchless rehabilitation to first of all save on costs and better manage those assets, but also provide significant benefits on the social impact, less detours and less impacts for the motoring traffic, which is obviously appealing to the asset owner as well. So in terms of the infrastructure needs, obviously I think everyone is pushing towards a much more proactive asset management program. The way to do that, in our opinion, is through better non-destructive testing, which helps to maximize those budgets. And obviously we're proud of the innovative technology that we're able to bring to help solve some of these infrastructure needs. So at this point, I'm going to ask Steve, our lead engineer, to kind of go through the specifics of the Inversa technology.
Hello, I'm Steve McCormick with Inversa Systems in the civil engineering arm of the company. We're going to talk a little bit about the Inversa approach to asset management, specifically to the problem with CMP pipes. As you know, corrugated metal pipes are considered to be flexible conduits, and as such, they're heavily dependent on the soil for their structural stability and service life. One of the things we know is that more and more clients are looking to a trenchless solution to avoid disruption of infrastructure or roadway service or other problems like that that are often faced by the asset owner. So the question becomes, if we're just looking at the interior of the pipe without addressing the soil structure, are we really getting our money's worth, and are we getting the maximum potential service life extension from these assets? And that's what Inversa steps in to deal with. Current inspection methods with regard to these type of assets are very typically visual and occasionally acoustic or knock testing. These are both good screening tools. Inversa uses them, but with visual inspection, what you can tell, obviously, is there are visual cues like corrosion, joint failure, misalignment, deformation, things like that, that can be easily documented. But you can't go beyond what you can see. Some people do acoustic testing, or knock testing, which is banging on the pipe, to try to identify regions of the pipe wall which sound different from the rest of the pipe. This is a good screening tool, but what we know from years of experience with this, it's subjective, and it is subject to a lot of false positives. In other words, very, very small anomalies can make a pipe wall sound hollow. So although it is a good screening tool, neither visual nor acoustic testing are conclusive as far as structural integrity and flexible conduits are concerned. Inversa has developed several technologies. Our lead technology is our Insight system, which is the first CAT scan for infrastructure. And many people are familiar with a CAT scan in a hospital environment, which, if you can imagine, it's a large donut and a human body slid into the hole in the donut. Inside that donut is a gantry, and on one side of it is a radiation source, and directly opposing that is a detector. So the radiation beam is shot through the human, and the gantry is rotated around to create a relative map of density and a cross-section view. Inversa's innovation was being able to do this from one side, so that we're no longer limited by the size of the hole in the donut for the objects we can examine. So this is the first time the CT scan has been taken out into an industrial environment. And what you can see there is the scanner gantryed against a piece of pipe, and you can see the image. The dark wavy line at the bottom is, of course, the steel corrugated pipe wall, and behind that is a void area, and further on into the image is the surrounding backing material. Inversa's innovation for the application of this type of tool is a three-part condition assessment. What we try to do is look at best practices in the industry when it came to our visual inspection, and we developed a very robust, highly repeatable visual inspection protocol. And for us, it is software driven, so that the idea is ultimately we can have a very, very consistent rating between various inspectors in various conditions. Ultimately, what we feel is that a well-done, highly repeatable visual inspection is an excellent piece of information. And when done consistently and in a repeatable fashion, even that information can be compared to subsequent inspections, and you can begin to trend deterioration of an asset. We went a little further and built a very robust protocol around acoustic inspection, where we test almost the entire interior of a pipe for acoustic anomalies. So what we know from our experience with acoustic testing is that when we bang on a pipe and it sounds solid, about 99.6% of the time it is. When it doesn't sound solid, all we can say is it's different from the rest of the pipe, and we don't know what's going on there. So what we do then is we locate these areas, suspect regions or anomalous areas, and we create a pipe map, which we'll talk about a little later, so they can be located. And these acoustic anomalies, if they're large enough and in consistent patterns, depending on the risk threshold of the asset owner, they will be selected for VCT imaging. And with that, we can tell exactly what's going on behind the pipe wall. It's conclusive, quantifiable, and also allows you to have a little greater depth of understanding, sometimes based on the geometry of the void. So what we do is, like I said, Inversa's approach to this is to do a visual assessment. And like I said, it's a software-driven approach. The idea is that we very typically begin with the road surface, guardrail, embankment, head walls if they're there. Then we look at stream alignment, scour. Then we go down the pipe barrel and we look for alignment issues, failing joints, corrosion, tipped or missing bolts, through wall corrosion, invert deterioration, and other things that can be assessed visually. These are all forced ranked in a 1 to 5 system. And then with that, we can begin to, a pipe that looks good can be tabulated. A report can be created based on the visual assessment, and if there is no need to further inspect, that can be fine, because we can do a large amount of pipes for an asset owner visually. Then if there is reason or suspect reason, We very typically do an acoustic assessment of the entire inside of the pipe. With that, we then create a next phase of reporting where we create a pipe wall map. We look at the location and size of these anomalies, and if they are of concern, then they can be further investigated. Finally, we end up with the deployment of the BCT imaging system, the InSight system. When we have acoustic anomalies that have been located and are in suspect regions or are of concern to the asset owner, they will be imaged. The scanner is roughly the size of a golf bag, and it's placed against the pipe wall closely. And you can see in the sort of lower left-hand picture, you can see the scanner placed up against the wall. We use just a timber gantry. And we can locate that scanner in any clock-face position around the pipe, depending on where the anomalous region is. Then the radiation source is deployed into the scanner, and the scanner is operated from a laptop remotely. So while the scanner is operating, we are not in the pipe with it. We're outside the pipe using a laptop to control it, and there is an image created in real time as the scanner is operating. Very typically for culverts, it takes about 8 minutes to create an image. And the image is very typically 10 inches wide and 10 to 12 inches deep. As I said, when we begin to pull all this data together, one of the things our software does is it creates a map of the pipe wall, in other words, a representation of the pipe wall, which has dimensional information. And as you can see, there are small dots on it that are labeled typically V and a number for visual anomalies or visual cues. Then there are large dark squares, which are acoustic anomalies. And then if there was a BCT image taken, it will be within the acoustic anomaly. So you see the red dots marked BCT where the images were taken. So what we try to do is compile all of this information into a representation of the pipe. And this is an abbreviated version. We have an overall image, which usually includes the full segment of pipe. Then we break it down into more manageable segments. So you can tell this one is, from station 30 meters to station 45 meters in the particular pipe that this was taken from. When we begin to look at this image holistically in a larger big picture, and we begin to look at where the acoustic anomalies and voids are located, we can often infer the failure mode of the pipe. In other words, oftentimes we'll see void areas in the haunches of the pipe, and very typically these indicate that there's a flow-related issue, or water is either flowing under the pipe or is leaving the pipe from through-wall corrosion or faulty joints and then flowing under the pipe, removing the fine materials and creating an unsupported zone under the pipe. There are other failure modes we've noticed where we can see sometimes voids are both above and below the spring line of the pipe, which very typically indicates water is infiltrating from the surface down, hitting the pipe, removing the fines from along the pipe through this water flow pathway, and very typically that goes to the invert of the pipe and flows out underneath the pipe. So a lot of information can be gathered from the pipe map. Very often when we're dealing, especially in roadway culverts, it's more difficult to do with stormwater systems. We provide a pipe profile plan, which is gives you the burial depth, the geometry of the embankment. If it's possible, we survey inside the pipe to give you both vertical and horizontal alignment. And be able to show any inconsistencies like sagging in the pipe, different things like that. So this also is another piece of information that can be very valuable to the owner in assessing what needs to be done with a project. Here are some very typical BCT images, and on the left you'll see that there is no void. So you can see at the bottom of the picture the corrugated metal pipe wall. Behind it you see very consistent density material with no void spaces in it. In the middle, you see a transition to void. So what you'll see is the pipe wall at the bottom, and again, soil to the left, and the soil density beginning to drop dramatically until you see a black region right inside of the pipe wall. So that's the fines being washed out. There's very little material left there, and it's almost completely washed out up against the pipe wall. And then if we go to the right side, you'll see a complete void where we look through the pipe wall. The space in front looks exactly like the space in back. One of the things we often say, and it's something that we discovered over time ourselves by dealing with some of the engineers we deal with, is that the geometry of the void is often very telling as well. In other words, with a little bit of experience, we've realized that soft, sandy type soils tend to fail in a very straight shear wall behind the pipe when there's a void present. Often if they're very jagged lines, we know we have very typically glacial till or well-compacted granular material. And in this case, you can see a water piping channel entering the image from the upper left. And in this particular case, it was for a City of Toronto, and when we took this image, we thought nothing of it. The engineers responsible for the large pipe we were looking at said, well, wait, we think there's a stormwater pipe where that water channel is pointing. And in fact, there was a smaller diameter, 24-inch, I think, a concrete pipe that had a failed joint. The water was running through that failed joint, flowing down through a little bit of a weak spot in the soil, hitting the culvert pipe, and ultimately causing a void behind it. And this is the start of that void. That void turned out to be many meters long and many meters high, so it was a very substantial segment of the wall of that pipe that was totally unsupported and under 6 lanes of traffic with about 20 feet of cover. That pipe has since been rehabilitated. The annular space was grouted. The pipe itself was in pretty good shape. We understand from the owner that it was a $7 to $10 million excavation. It was easily accomplished in a very short period of time. I think the contract was let for about $900,000. So substantial saving for the owner by being able to know where the flaw in the soil is, what's causing it, and then being able to go in and remediate that fault later. In other words, stabilize the soil with grouting, ensure that none of the infrastructure above it had to be shut down, very low impact, but a great example of a nice catch. In other words, a good asset management program followed up by good inspection where required was able to point exactly at the problem. The problem was described in such a way that could be easily remedied. The remedy was made, and there was a large cost saving for the owner. So what we can say is Inversa System, basically what our goal is to conduct conclusive structural analysis of assets, prioritize critical assets. In other words, begin working with the asset owner to develop a good management strategy. Very often we'll look at large numbers of pipes in visual and acoustic testing only. Then we will sit down, consult with the asset owner and say, these are of these assets we looked at, here are the few that are of highest concern. How much budget do you have to deal with it? Because often in the real world, there are very, very hard budget limits. And they'll say, well, we have enough to deal with 3 pipes out of the 10 you looked at. So which are the worst 3? And that's what we mean by prioritizing critical assets. In other words, looking at the 3 at highest risk and allowing the owner to develop a rehabilitation program that addresses the assets they can't afford to deal with at this time. Like I said, a good visual and acoustic program can allow you to start to detail baseline information on these assets. You can begin to compare subsequent inspections if they're done in a highly repeatable, robust fashion. And then you're beginning to look at monitoring these assets and even trending the deterioration over time so that you know when an intervention is best done. And of course, when this is done well, this increases safety to the asset owner, safety to the users of the utility if there's a road above it or any other infrastructure. One of the other things we do sometimes is deal with post-construction QA/QC. In other words, we can look at pipes to see if they are indeed buried correctly. Often we've looked at post-line pipes, in other words, pipes that have been previously lined, conducting inspections of the annular space to ensure that there is grout in the annular space where it is supposed to be. In other words, is the line pipe well supported as designed? This is something we've done primarily for the Army Corps as part of both an ongoing research program and a program they're using to tighten up their specifications for pipelining. Here's I'll go through a couple of brief case studies. This is a recent Quebec up here in Canada, where we were dealing with a large diameter length of corrugated metal pipe that was a shared asset. In other words, part of the pipe was under municipal assets. The other part was under a provincial highway, a 4-lane arterial highway into Quebec City. This is an older version of our pipe representation, but if you look on it, you can see where there were visual anomalies, where there are small squares, where there were acoustic anomalies down in the haunches of the pipe, and then ultimately the black dots where there were VCT images taken of it. So we began to look at this. The concern was there was some severe deformation of the pipe, but it was highly localized. In other words, of the 180 meters of this pipe, there was really only about 4 meters that were really of key concern structurally. So we did a robust test. We did a visual acoustic testing completely. We did BCT imaging where it was needed. What we did is we were able to locate 4 acoustic anomalies, 2 of which I believe were void areas, which were easily remediated, and we were able to help the owner develop a program to rehabilitate this pipe, which included some chemical grout applications in key locations in order to stabilize the soil around the pipe, 1 structural repair, which in this case included a tunnel plate type structure inside the pipe, and then a corrosion-resistant coating. With all of these things handled, the client went from dealing with about a $5 million project down to dealing with a $500,000 project that would address only the parts of the pipe that were failing and really deal with only the segments of soil supporting the pipe that needed to be stabilized. And then, again, add a corrosion coating, which allows the useful service life of this asset to be extended greatly. And also, like I said, a structural repair in 1 very specific location to deal with that type of failure mode. Like I said, we developed on the outflow part of this pipe from 156 meters to 180 meters. It was on a very severe downslope. That segment of the pipe actually wasn't able to be rehabilitated, but what we were able to do with the client, since the outfall was in such an advanced state of disrepair, is we were able to make recommendations on a monitoring program. In other words, we were able to say, here's the features you need to measure. You need to measure them every 3 months. Here's your survey measurements you need to take. In other words, here's where the location of the pipe is. If it shifts from that, then this is a very high concern. So not only did we help the client locate the problem, point them in the direction to rehabilitate the problem, fix the part of the pipe that can be easily fixed and safely fixed, extended service life, but even on the segments of pipe, the outfall in this case, that weren't easily fixed, we were able to recommend a monitoring strategy so that they'll know exactly when they do have to intervene. Another case study is the City of Guelph in Ontario, Canada, where we dealt with a large stormwater project. And again, some of this pipe was under municipal infrastructure, in other words, very dense residential neighborhoods. Some of it was shared assets on a provincial arterial highway into the city. We looked at many, I think there was 17 segments of pipe we looked at in this project. Of the 17 segments, I believe there are 4 segments that were of concern. So what we were able to do again is go into a visual and acoustic inspection, locate the areas of high concern. Acoustic anomalies were mapped and quantified, and ultimately BCT scanning was done in order to ensure that the voids supporting the pipe were, that weren't supporting the pipe were located and could be filled. And this is exactly what the owner wanted to do. They wanted to extend the service life of this pipe for minimal cost, so they wanted to point their rehabilitation budget exactly where it needed to be. So we were able to look at this and say, for now at least, with an ongoing inspection program, you have good baseline data. There are really only 4 segments of the 17 segments of this pipe that needed to be dealt with immediately. The other ones, maintenance can be deferred and monitor them. You have good baseline data, and if you see any changes in the data you're collecting in subsequent inspections, then let us know, and we're happy to go back. We can go in with the BCT equipment and see if these voids are getting larger or if new ones are forming and so forth and so on. But you'll look at some of the images from one segment of pipe there, and what you'll notice is a lot of them have voids, some of them don't, some of them have very small voids. But one thing I'll tell you is that all of these suspect areas sounded equally hollow. In other words, it's a very good example of how acoustic hammer testing is an excellent screening tool, but not conclusive. And what you can see is different geometry in the voids forming behind the pipe wall. Some of them are very straight, which is the soil wall, which is, like I said, very indicative of softer sandy silt type soils. And some of them are more jagged. Usually that means that there are granular materials in it. So like I said, 17 sections of pipe. There were really only 4 that needed to be addressed. There were 44 acoustic anomalies. Of that, 31 were imaged. In other words, it's a great example of looking at a large system for the owner, identifying the areas of key concern that need to be dealt with quickly, addressing those with the information you need in order to rehabilitate them. In this case, it was sort of anti-corrosion coatings or semi-structural type solutions, but the key thing is those pipes needed to be well supported, and the voids that were located could be grouted, filled, and stabilized, which goes a long way in overall stability of this pipe system. So this is a great example of a large system where we looked at the whole system with visual and acoustic screening, determined where we needed to do BCT imaging, took the BCT imaging, and with that total 3 tiers of inspection, we were able to focus the owner's dollars only where they needed to spend them. An interesting one we did was we did some work in Louisville, Kentucky with the Army Corps of Engineers. We were looking at some gate structures. In other words, pipes that travel underneath the levee from both the river side to the inland side. These pipes have a gate structure or a big check valve in effect. In other words, in storm events, the valve can be closed to prevent river water from coming inland. In normal weather conditions, the valves are open. Rainwater can flow out to the river. What we found is some pretty interesting and consistent flaws in these pipes where we were seeing acoustic anomalies at the spring line extending both above and below it, which is not typical. So we did some VCT imaging on these to try to figure out what was going on with these pipes. And what you'll see here is some of the imagery we took, where you can see the pipe wall, and you can also see in the soil an imprint of the pipe, which was not unique because at the time these levees were built, the Army Corps felt that high clay content soils were very stable in wet storm conditions, and it was a good material to build levees with. So what we found when we looked at this is that seasonally the moisture level in the clay goes up and down. When it goes down, the clay contracts off the pipe a little bit. So seeing an imprint of the pipe is somewhat expected. What we didn't expect is seeing the imprint of the pipe and the pipe not lining up. And what was happening here is, as it turned out, there were some heavy corrosion in the invert of this section of the pipe, and what it had done is sort of buckled in on itself on the bottom when the clay expanded. So the clay was pushing it from the sides, and when the clay retracted, it pulled away from the pipe, left a space, and there was enough space in this case that the pipe was actually traveling downslope through the levee. So this is a really interesting example of how the geometry of a void can often lead to understanding the root cause of the failure. And when we understand the root cause, then we can develop an engineered solution. In this case, the Army Corps very typically likes to use cellular cementous grout. And in this case, I think they worked with a bentonite slurry that more accurately simulated the conditions of the native soil, so that it would act more like that in the long term, and they were able to fill the void behind these pipes with that type of material, and then they were able to go in and do a structural repair on the pipe. So again, like I said, a very interesting example of how the geometry of the failure can lead you to a really well-engineered rehabilitation program that addresses that failure mode. Here's another one we did for the Army Corps where we looked at a previously lined HDPE pipe. And if you look in the upper left of the image, you can see that there's an HDPE liner, a very well supported, consistent density material behind it. On the right, you can see in the bottom there's an HDPE liner, a void, and then a wavy line behind it, which is the original corrugated metal pipe through the levee. What the Army Corps was trying to do is understand if their grouting protocols were yielding the type of results they expected. And in this case, looking at several of these line pipes, we found a consistent flaw where on inlet side 12 o'clock there was a void, and outlet side 6 o'clock there was a void. And what was going on is that the several liners were being grouted in the same day, and they weren't allowing proper settlement time for the grout they were pouring in to seep through any inconsistencies in the invert of the hose pipe, different things like that. So it was neither a failure of the materials, the technique, nor the contractor. It just was an incomplete understanding of what's required to fill these voids. And what they've subsequently done is now they will often grout multiple pipes a day, but they'll also insist that with a 24-hour time limit, a second tier of grout will then be installed after the first tier has had time to settle into place. So like I said, an interesting look into a failure mode that they suspected was going on, but really had no way to fully understand it, and take a little bit of information, tweak their technique to get a much more consistent, better result, which they're much, much happier with. So like I said, this was the Louisville levy program with the Army Corps, and ultimately at the end of this, the Army Corps of Engineers has decided that Inversa's Insight system is a commercially viable product for locating voids through CMP pipes. So I guess in conclusion, what we can say is visual and acoustic and mapping alone are excellent screening tools, but they're not enough to put together a well-thought-out, well-engineered rehabilitation program for a pipe. Current inspection methods we know can both under and overestimate a culvert condition. Conducting a full structural condition assessment gives the highest possible degree of confidence for either the continued operation of the pipe, monitoring, or for developing a rehabilitation plan to get the best possible outcomes for the asset owner. So in other words, our BCT equipment, when used in conjunction with a good asset management integrity approach, allows you to avoid costly replacements. You can defect nonconformancies early. More importantly, trend deterioration, so you're repairing only when it's necessary and to maximize safety. You can quantify necessary repairs. You're not only looking at voids, it's possible to estimate the volume of the void. This allows you to increase safety, reduce maintenance costs, repair voids prior to trenchless rehabilitation, which is something that's often overlooked in a lot of rehabilitation strategies. We think it's vitally important because you can ultimately spend a lot of money to repair an asset and still have the soil fail around it. Just like we saw earlier in the URETEK picture where you could saw the soil fail around a manhole and the manhole standing perfectly intact. So this is really what we're trying to avoid. So really we like to say that we can confidently optimize asset lifespan with a comprehensive approach to this, an asset integrity management approach. Often, like I said, looking at multiple assets, prioritizing them for the owner, and ultimately helping them develop an excellent, well-engineered rehabilitation plan with the best possible information that can be provided.
So that's it for the Inversa part of the presentation. Ori?
That's very good, thank you. Robert, you have some questions to ask Inversa.
Certainly do. Okay, so I'll just run through this, and just to quickly note, there's the questions area within your webinar tool area. So if you do have any questions, please type them in there, and we'll make sure that they get asked for the group. So, so first of all, what other pipe materials other than CMP, and how small of a diameter can be scanned using the BCT?
We've focused our shot at the market on really a currently unmet inspection need. BCT equipment is very well suited to corrugated metal, plastics, thin composites, and probably up to about a ½ inch steel pipes to look through. Concrete, we're often asked about, is very, very difficult to deal with from a radiation standpoint. The intensity and type of radiation required would create a very, very large exclusion zone, so it wouldn't be practical to deploy in the field. The type of radiation we use is very commonly available isotopes, and they're very often used in weld inspection radiography for, say, gas pipelines, things like that. And when we're underground, the shielding the ground provides is excellent. In other words, we can walk out of the end of the pipe, walk to the side, and we're very, very safe. So again, I guess the recap is corrugated metal because can't be done with GPR or other technologies. Plastic pipe is an excellent, or previously lined pipes where you have composite type structures where they've been lined, sprayed, coated, CIPP, things like that. So those are all possible to do.
And just to clarify on and answer the part about size, is about 900 mil, 30 to 36 inch. Person entry is required to use the scanner.
Okay, thank you. Does it matter the type of material that is behind the pipe in order to see voids, sand versus rock,
What we
etc.?
can say with that is CAT scan technology is a relative map of density. So provided there's at least 10% difference in bulk density of the materials, they can be distinguished on the image. So yeah, often, you know, if it's really well compacted sand, often we can see rocks in loose material. So like I said, it's a relative map of density. So long as there's that 10% difference in the density of the materials, they can be distinguished.
Okay.
And it doesn't really matter what material they are.
Okay, great. I had another question. I think it was just answered, so I'll just confirm it. But it's, what is the minimum size pipe the survey of existing conditions that can be done on? And I believe that was 30 to 36 inches, if that's correct?
That's exactly correct, yes.
Okay.
We were currently require man entry because we physically place the scanner head where we want to look.
Okay, great. Thank you. Next question is, what is the, oh, let's see here. That's regarding the Centripipe, but I'm going to stay on this part for a moment. Why would you scan if you're going to rehabilitate anyways?
Because typically, like I said, with attention to corrugated metal pipe, the soil structure really is the larger part of the structural component of the composite structure. In other words, after all the soil has been in the ground, compacted, well placed, and had a freeze-thaw cycle or two through it, really the pipe, a lot of pipe guys don't like to say this, but it more or less becomes an abrasion-resistant liner for the very stable hole you've created in the ground. So you can spend a lot of money to rehabilitate a pipe, and if you don't address the soil, you really haven't addressed it structurally. All you've done is create the potential for that really well-lined pipe to fail again and have the infrastructure or the road above it still come down. So really, and I guess a really great example was in the URETEK presentation where you saw a really well rehabilitated manhole, very, very stable, and all the soil around it fell down, and it's still a catastrophic failure, even though the manhole was fixed very, very well. And it's the exact same thing with these type of pipes. So they're addressing the soil that's supporting that pipe. You've really only got a half of the equation dealt with.
Okay, great. Now this sort of has been, there's a two-part question. The second part I think has been discussed, but I guess we can address again. Can we plan, so the first part is, what is the cost of inspections and screenings? And then the second part of the question is, can we plan to line without doing the inspections or screenings at all?
Yeah, you can plan to reline. I guess I always look at it this way. If you can imagine a scale, on one side there's money and on the other side there's risk. If you don't have any money, you have to bear a lot of risk. If you have some money, you can bear a little less risk. So I always look at it in a sort of a balancing act. Oftentimes we deal with projects where there are very limited budgets. So what we'll do is we try to do some relatively inexpensive screening, in other words, visual and acoustic testing. That can be done quite fast, you know, and at a reasonable cost. It's probably very typical, depending on site conditions, location, and a lot of other variables. So this is really a ballparky figure. But let's say between, we can probably do 300 to 500 lineal meters of large diameter pipe in a day. And that day for visual and acoustic would typically cost $5,000 to $7,000. And that would include all the reporting, the pipe maps, and everything that's involved with that, so the client would get those full reports. With the radiation scanning, that's very typically an additional $10,000 a day. And with that, we can do about, very typically, 20 scan sites per day. So it's very typical for us to look at a large program where we'll look at many, many pipes. In other words, we may look at 10 pipes for, I don't know, let's say, you know, $20,000 for visual and acoustic, and then of those 10 pipes, we might identify 2 or 3 of concern, and then and only then will we require the more expensive VCT scanning at the end to get all of the information you need, because that's really all the owner is prepared to deal with anyway. So we try to work very, very closely with owners and what budget is available, what level of screening they need to have to make a decision, and really where they need to spend their money. So there's a lot of variation in cost. It's like being a contractor and saying, how much does it cost to put a culvert in? Well, you know, it really depends where you're putting it in and the other sort of issues you have to deal with on site. But that's kind of ballparky, I guess.
Okay, thank you. This is more oriented towards Centripipe. Does the thickness of the Centripipe affect capacity?
Robert, is that the last question?
No, there's quite a few more.
Okay. Centripipe is applied in 1/2-inch lifts, so each or pass, I should say, and so you'll have a project where maybe you'll have a 1/2 inch or you'll have up to an inch. It just depends. But the Manning's coefficient is 0.014, so that's the advantage of using Centripipe. Is you do not reduce the hydraulic capacity. You're still putting in a concrete surface, if you will, for the hydraulic flow, and with very small diameter change, only be a 1/2 inch across the entire diameter, then very small reduction, and therefore our hydraulic capacity remains very close to the same.
And a follow-up to that is, what is the cost compared to replacement?
We've got different examples that show a significant size, similar to how Steve was responding on the Inversa and the cost. Every job is different. If it's a shallow application, obviously remove, replace could be less, could be similar in cost doing the Centripipe, but then if it goes deeper, or there's 4 or 5 or 6 lanes of highway traffic above, it's a significantly different scenario. So in situations where you've got a lot of traffic above, maintenance of traffic, rerouting, then those are some of the other items that come into play, and that is when Centripipe is really the right application, because you can make a like new pipe but not have to impact all the ground above.
Okay, thank you. Yes, so one more question regarding the BCT scanning. Can BCT scanning be used conclusively for HDPE pipes?
Yes, it works very, very well on that. It's a reasonably low density material. So yeah, absolutely.
Okay, I have it's a bit more of an announcement, which is perfect for us. So please take a moment. I have no more questions left, so if you have any more questions, please take this time to submit those. But I'll go ahead and make this mention. This is for the Ohio Transportation Engineering Conference, which we attend every single year, so it's certainly a conference we support. But they just had somebody submitted an announcement that said, Ohio Transportation Engineering Conference. It's a 2-day event where numerous engineering topics are presented every year in October, and abstracts are accepted for the 2016 conference from February 29th to April 1st in 2016. So that's an announcement for URETEK. We support that conference, so had no problem certainly mentioning that. As I don't have any further questions, unless anybody's got any more to submit. I'll give 1 moment for that. Okay, I did have one more comment in here that asked if we could submit some cost information. Certainly. We'll be submitting an email shortly after this webinar that will help with any kind of, that'll be a short survey on any type of follow-up questions that you may have, but also for our PDH certificates and a link to this webinar recording, as well as the presentation materials. So within that, if you have any questions such as desires for cost information or anything like that, please let us know there, and we'll be certain to connect someone with you to give you any items such as that. So, and that seems to be it for the questions.
Well, thank you, Robert, and thank you very much for everyone's attention. Greatly appreciate it. Yes, Inversa as well as URETEK Holdings, we would be more than happy to give cost estimates for any particular project that you do have. We've got sales engineers throughout the country who could personally meet with you, as well as handle a lot of things over the phone and email to get you the answers. Really appreciate your time. It is noon Eastern time, so I want to be respectful of everyone's time getting back to work. And thanks for hearing about the Outside Inside as well as the Inversa technology. We are doing monthly webinars, and our next webinar will be on November 13th. We are partnering with University of Wisconsin. They have put together a report. Right now it has been done in the lab only, and then pretty soon they'll be doing field testing. But what the thesis of the test is that injecting chemical grout into existing rail ballast, which is the aggregate underneath the rail, by injecting chemical grout into the existing ballast, it actually will perform better than brand new ballast. So very rarely do you have a rehabilitation effort that is less expensive and performs better than brand new. But what's happening in the lab test at University of Wisconsin College of Engineering is it is in fact proving to be true that the existing rehabilitated solution is performing better. And so there is a paper and a study that has been underway. So we will get an update from Dr. Tinjum, who is a professor for University of Wisconsin. That'll be November 13th. So please join us for that webinar, as well as invite any of your colleagues who are in the rail industry. We greatly appreciate it. And please stay connected with us to learn more about the different projects, the different applications, the different solutions that we are working with each of you on, and providing solutions every day for you and your customers. So thank you very much for your time, and have a happy Halloween this weekend with your families. Thank you.